discussed about interference sound. So today we continue with sound, and next we'll discuss standing waves. So let's begin. So we had seen the condition for interference of sounds, that sound waves coming from sources of equal frequencies overlap to create that effect of interference, and there's the phasor diagram method for addition of amplitudes. Right? Condition for constructive and destructive interference. We had discussed those kind of things. Okay, now the next aspect of superposition of sound waves, the superposition effect we'll see is standing waves. Or stationary waves. In sound. So these can be created by the superposition of two one-dimensional sound waves traveling in the same medium but in opposite directions. That's one way of creating it. So we have two different sources, like two tuning forks, source S1 and source S2 of same amplitude and same frequency, which are creating waves traveling in the opposite direction, pressure waves in the opposite directions. Their superposition will result in standing waves. So the pattern of pressure variation is time that we'll get. So if this is our x-axis. So from source 1, the speed of sound, suppose, is a gaseous medium, that kind of situation. Yes, transverse mechanical waves was over long time back, Jagannath. Before we started sound, that was a couple of lectures back. Yes, okay. So the net pressure variation now comes from this. So just like we had seen superposition of transverse waves in opposite directions of same frequency and amplitude to produce standing waves, we'll see the same here. nothing. Okay. So suppose I is equal to and write it as the amplitude. So we have position dependent amplitude, where the amplitude can vary between 0 and 2p naught. So where the amplitude is 2p naught, we call them the antinodes. Call them the nodes. No, we are doing standing waves. Interference is completed in the last lecture. Okay. We've discussed those 2 or 3 variations of questions also. Now we are doing the next thing in superposition of sound waves, which is standing waves or stationary waves. And all this is like the mathematical treatment is identical of how we are done in transverse waves. Okay, so it's just the difference is instead of dealing with transverse displacement wave y equal to a sine omega t minus kx type, you're dealing with pressure waves that p is equal to p naught sine omega t minus kx. Yeah, for the sake of Okay, people. So next up, we will see standing waves created by resonance in an air column. Chaos. Traditionally, we also call these organ pipes. The term organ coming from the musical instrument. Built using air pipes for sound. Church organs. So in this, we have two categories of organ pipes. The first category is called open organ pipe. So an open organ pipe is a thin cylindrical pipe with both the ends open. So it's a cylindrical pipe such that length is large compared to its radius. And both the ends are open. What will happen is for any resonant mode, the air molecules at the open ends will have zero pressure change. They'll have zero amplitude. So there'll be pressure nodes. So the fundamental mode will be one where the two open ends are consecutive pressure nodes. And in between, we have a pressure antinode. So in the fundamental mode, L is equal to lambda by 2. So the fundamental frequency is 1 by 2L into speed of sound. So this is one important formula and concept. Okay. Fundamental mode of vibration or fundamental mode of resonance for an open organ pipe. An open organ pipe being a pipe which has a cylindrical pipe which is open at both the ends. So the open ends act like pressure nodes because there is zero variation of pressure. because the air there is in contact with atmospheric air. So cannot be under any kind of volumetric stress. So the pressure variation is zero, or the pressure amplitude of the standing wave is zero at these 2 points, the open ends. So if they are consecutive nodes, okay, then we have the longest possible wavelength or the least possible frequency, which is called the fundamental frequency. So this is just like the vibration of or the creation of resonant moves in a string, which has a rigid boundary at both ends. Remember earlier, a string which is tied at both ends. There the formula of fundamental frequency was 1 by 12 into square root of tension divided by mu, or that is speed of transverse wave. Here you just have to replace the transverse wave speed with the longitudinal or sound wave speed. Rest everything is the same. Okay, Jagannath, I'll scroll up. In the earlier part, we saw the creation of standing waves by superposition of waves traveling in the opposite direction. Okay, and we explored the general equation of a standing wave like this. Now we are seeing the application of this concept in a situation where there is resonance created in an organ pipe. It's 5 by 2 beta. And you can see how that is coming. That is coming from the formula of sin A plus sin B. That is 2 sin A plus B by 2, okay, into cos B minus A by 2. So if you just apply that formula, you'll understand that that term is 5 by 2. Even this one should be 5 by 2.
Answer.
Okay, so okay, so this is done, I hope.
Yes.
Okay. So moving on now. So if you look at the first overtone mode, okay, the fundamental mode was where the waves, the two ends are consecutive notes, and there's only one antinode in between. So the first overtone mode is the next possible mode possible. Next possible pattern with minimum number of nodes and antinodes. So in the fundamental, we had two nodes and one antinode in between. So the next possible in the harmonic series, the first overtone mode, that will be the mode in which we have three nodes and two antinodes. So increasing one pair of node and antinode. So in this mode, we had two nodes and one antinode. So now in the next one, we'll have three nodes and two antinodes. So first overtone mode. The first overtone mode, the two open ends are still nodes, but now we have one more node which will be at the midpoint. So the sequence will look like this: three nodes, so two antinodes in between. So lambda is reduced to half of what it was in the previous fundamental mode. So we have lambda is equal to L. So frequency of the first overtone becomes 1 by L into speed of sound, or it becomes the second harmonic. So this is just like the string tied at both the ends. It's the same sequence that we'll get overtones. Only in the formula, the speed of traveling wave as square root, transverse wave as square root of tension by linear mass density is replaced with speed of sound, which is square root of gamma RT by. Every overtone mode shikhar is the next possible member of the sequence of frequencies. So fundamental is like the zeroth overtone, you can say. Okay, but we call it fundamental. First overtone is the next highest frequency. Second overtone is the next highest frequency. So it's a sequence of resonant modes. Okay, and each one of higher frequency is the next highest overtone, like that. So second overtone mode. And this there will be one more pair of node and antinode. So there will be 4 nodes and 3 antinodes in all. So now the length of the open organ pipe will accommodate 3 loops instead of 2 loops. Something like this. So 4 nodes and 3 antinodes, but more importantly, see this is becoming 3 times lambda by 2 because there are 3 loops, so to speak. Loop is the node to node distance, which is lambda by 2. So now L becomes equal to 3 lambda by 2 in the second overtone mode. So frequency of the second overtone becomes 3 by 2L, speed of sound. So the second overtone mode is the third harmonic. So now if we extrapolate like this, we have the formula for the nth overtone mode. So in the nth overtone mode, L will become n plus 1 lambda by 2. So frequency of the nth overtone will become n plus 1th harmonic of the fundamental. Okay, so the resonant modes, they form this kind of a sequence. Okay. So as a simple example, we have an open organ pipe of length, let us say 20 meters, and speed of sound is 340 meters per second. So find the fundamental frequency, the frequency of the fifth overtone mode. Okay, so let's quickly work out this question. So it's completely formula based, this type of question, as you can see. To just understand that the fundamental mode will have a frequency given by the formula 1 by 2L square root 1 by 2L into speed of sound. So it's directly given over here. So 1 by 2 into 20, 340. So that is 340 by 40, 17 by 2, or 8.5 hertz. Okay. So the frequency of the fifth overtone mode will be 6 times. So 51 hertz. So this is the fifth overtone. This is the fundamental. Okay, now next we'll look at the second type of organ pipe for resonance, which is called the closed organ pipe. Now, what you have to remember about this is closed organ pipe means that one end is closed and one end is open. It's not that both the ends of the resonant column are closed. Okay. So this is just a matter of nomenclature that we actually don't discuss a case where both ends are closed. Okay. One of the ends at least has to be open. So let's say this is the open end, and the other end, it may be closed in the case of closed organ pipe, or it may be open in the case of open organ pipe. So these are the two. Okay, so the air at the closed end, it forms a pressure antinode. Now, why it forms a pressure antinode? Because the air at the closed end cannot displace. So therefore, if it cannot displace, the pressure variation or the volumetric stress is maximum. So therefore, it's a pressure antinode because it has maximum amplitude. Okay. Whereas the open end, it acts like a pressure node. Because it has zero pressure variation. So this is like the case of the string, which had one rigid boundary and one flexible boundary, that kind of situation. So here again, the difference is that in the fundamental mode, open end will be a node, pressure node, but the other closed end will be a pressure anti-node. Okay. Something like this. Okay. Should be lambda by 4 because they're consecutive node and anti-node. So lambda is equal to 4L. So frequency has a different formula for this fundamental frequency. Instead of 1 by 2L, it is 1 by 4L into speed of sound, or 1 by 4L into square root of gamma RT by. So like that, now the first overtone mode, that will be one in which we have, instead of one antinode and one node, we have two antinodes and two nodes, because now we have this kind of sequence: node, antinode, node, antinode. So we basically have 1.5 loops. This is lambda by 4. This is lambda by 2. The length of the pipe becomes lambda by 2 plus lambda by 4. So that is 3 lambda by 4. So lambda is 4L by 3. So you can see wavelength has become half. So frequency will become 3 times. Or first overtone mode is the third harmonic of the fundamental. So we will see as we move on in this that this forms the resonant mode series, which has only the odd harmonics. The even harmonics don't exist. So you need to remember these two cases very clearly. Okay. Open organ pipe, both the ends are open, so all the harmonics exist. So the general formula is nth overtone is n plus 1th harmonic. Okay. So first overtone is second harmonic, third overtone is fourth harmonic. Okay. Like that. Whereas in the case of closed organ pipe, one end is open and one end is closed, so only odd harmonics exist. So first overtone becomes third harmonic, second overtone we'll say will become fifth harmonic, and in general the nth overtone mode will become 2n plus 1th harmonic. Just make a note of this people.
क्यों? साइकिल दिख रही है। हमें निचले ऊपर टॉप कौन सा पहना था? इनको मैं आपको बता दूं। वो देख रही है।
Okay, so let's understand the sequence of overtones. So like that, now the nth overtone mode. Okay, now something closely related to this is an experimental method. So in this experiment, what is done is that we take a glass tube like this, and we have a tuning fork of known frequency. Now, if the air inside the glass tube resonates that is with the tuning fork, that is the frequency f of the tuning fork equals to a frequency of the resonant modal series for the tube. So if this happens, the meaning of resonance is this, that the frequency of the tuning fork if that equals to one of the resonant modal frequencies for the tube, then on sounding the tuning fork, a louder, comparatively louder sound is heard. So this phenomena is called resonance, okay, as you know. So now what we do is now slowly water is poured into the glass tube. So as the level of water increases, at certain values of its height, resonances occur. By measuring these values, the speed of sound can be determined. So this is an experiment that is actually there at your practical physics 10+2 level, but I don't know when you people will get to do all the practicals and also just explaining the experiment in detail. Just make a quick note of this concept related to the experiment. We'll discuss the numerical part involved next.
Sir. Hello, sir.
Yes.
Sir, why are the overtones formed?
Why are the
Overtones formed.
sorry overtones what?
Sir, why are the overtones forming?
If the frequency of the tuning fork is equal to one of the overtones, then the process is resonance. There's easy transfer of energy from one source to another medium because the frequency of the source matches the resonant frequency of the medium. That phenomena is defined as resonance.
Okay.
Okay, so now let's understand how the resonance is created. So basically, as we fill liquid in the tube or water in the tube, so initially it is empty, and let's say it is not resonating. Okay. So we are hardly hearing too much sound from the tuning fork. So we gradually start pouring water, and let's say when the water level reaches here, the first resonance is heard. So H1 is the level of water for the first resonance. So that means what is happening at that point of time, the natural modal system is such that this length that is in this L minus H1, it is some mode like this. Okay. We don't know how many nodes and antinodes are there in between. but the two ends are okay. So it is, let's say, so this is corresponding to the nth overtone for the air column of length L minus H1. Okay. Now next we again, the water level is slowly increased. So basically initially from H equal to 0, the water level is increased until the first resonance is observed or heard at H equal to H1. Now, from this point, after noting H1, again water level is slowly increased until the second resonance is observed at H equal to H2. So at that H2, what will happen is that we compare alongside H1 now. Let's say we've increased the water level to H2, but resonance is heard now. So even this point is an antinode for the same tuning fork's frequency. So this distance from here to here, it must have been antinode to antinode. So it must be lambda by 2. Okay. So at H equal to H2, what we hear is that this must be similarly. If that same sequence is repeated, then L minus H3 will correspond to 2 times N minus 2 plus 1 lambda by 4. So effects. So basically now you can see from this that the difference in water level for any two consecutive consecutive resonances that we'll see will be equal to lambda by 2. Next one now will occur at NH3, such that again this point has to be an antinode, this point has to be a node for the corresponding frequency of the tuning fork. So again, this is lambda by 2. So you can see from here that F, the frequency of the tuning fork, is equal to speed of sound by lambda, where lambda is equal to 2 times H2 minus H1 or 2 times H3 minus H2. So by measuring the height of the liquid columns at various different resonant modes, we can find out the value of lambda. Okay. So basically, this experiment, what we do is by measuring consecutive resonances at h equal to h1, h2, h3, etc. Lambda is equal to h2 minus h1 or h3 minus h2, etc. So lambda is measured, and therefore speed of sound becomes f lambda, where f is the known frequency of the tuning fork. So from this now, the speed of sound is determined. So this is the complete description of the resonance column experiment for measurement of speed of sound. Okay. So this is part of your physics experimental syllabus, which is why I've discussed this in detail, because you can get a question in JEE where the data for this kind of experiment is given to you. Okay, let's say the first and second resonances height of liquid column is given, and the frequency of the tuning fork is given, and from that you are asked to calculate the speed of sound. So you must know the whole concept of this experiment. So make a note of this, please.
Sir, it will be h2 minus h1 by 2, no? No, sorry, lambda by 2 is equals to h2 minus h1.
Okay, so hope this concept of the resonance column experiment is clear to all of you. Okay. Now, when we actually do the experiment, there's just one minor added detail. In an actual experiment, the node, that is the pressure node, at the open end, that is the top part of the glass tube, actually occurs slightly outside. Slightly outside the tube.
Sir, you are on mute.
Yeah, I see what happens is now, as we are increasing the level of water, okay, the frequency of the tuning fork is not changing. Na? So the wavelength of the sound is the same. So if the wavelength is the same, the the number of, so what is actually happening is, like let's say in the first resonance, suppose the length of the air column was such that where the first resonance is occurring, okay, the length of the column is enough to accommodate, let's say it's the third overtone. Okay. So if it's the third overtone, there'll be 3.5, or let's say it's the fourth overtone. Okay, so that's 4.5 this thing. So this lambda is fixed now for this given frequency. So you can see that. So now if I increase the water level, I will get a resonance only when the water level reaches the next node. No? So when the water level,
Nodes, sir. Sir, it shows
oh
only
sorry,
on nodes or only on anti?
it's anti-node, sir. I have done it in reverse. Okay. So anyway, the water level for this should be here. And the top point should be a node, depression node. Okay. So now you can see that the first will be here. Okay. Suppose. So the next one will be when it reaches here. The next one will be when it reaches here. Because this shape of the wavelength is fixed because the frequency of the tuning fork is fixed. Okay. So that's why as we increase the level, the number of nodes and antinodes within that sequence becomes lesser and lesser. No? So the overtone number is decreasing. Is this point clear now, Ayushi? Okay, very good. Okay, so this phenomena that the actual pressure node does not occur exactly at the open end, but slightly outside the open end of the tube. This phenomena is called the end correction. And the end correction formula is given by, it depends on the radius of the tube. R is the radius of the glass tube. So actually, when you do this experiment in the physics lab, you generally use a vernier caliper or something to measure the diameter of the tube, and you incorporate that. So the effective length of the tube actually becomes the length plus the end correction. It becomes L plus 0.6 R. And the formula for resonant modes is that, L effective minus H1 is, let's say, so L effective minus H2, it becomes like this sequence. So on and so forth. So this concept of end correction is something important to remember. Okay. Now next aspect of sound we'll discuss is a phenomena called beats. It's very easy to understand, very simple. Okay. Finish writing this, then we'll discuss. Okay. So let's move on to beats. So as I said, beats is a very simple phenomena to understand. So beats occurs when there is superposition of waves, sound waves, but of different frequencies. So this occurs due to the superposition of sound waves of different but close in value frequencies. Best explained like this, that suppose we have one source which is creating sound of frequency f1 and another source which is creating sound of frequency f2, such that f1 is not equal to f2, okay, but f1 minus f2's magnitude is small. So by small we mean it is less than equal to about 5 hertz. So the difference in frequency should not be too high. In that case, the phenomena observed by a detector who is receiving sound from both the sources superimposed, that phenomena is called beats. So let's say this distance is x1, this distance is x2. So from source S1, okay, the sound heard is like this, okay, because omega 1 is 2 pi f1 and k1 is v by omega 1, where v is speed of sound that is common for both of the sources. And from source S2, the pressure heard is sound heard is so the superposition results in the net pressure variation of P1 plus P2. So K1 X1 is, let's say, alpha, the constant, and K2X2 is beta, which is a constant. So the net pressure variation will become 2P naught sine A plus sine B by 2. So that is into cos B minus A by 2. So just make a note up to this step, then we'll discuss the next one.
So
Yes,
how do we know that they have the same velocity?
because they're traveling through the same medium, na, beta, air.
Okay.
Remember that speed of a wave, whether it is transverse or longitudinal, that doesn't depend on the source. That depends on the medium. So waves
Okay.
propagating through a common medium. Yeah, actually these formulae are reversed. Here. So now this alpha plus beta by 2, this is also constant. Let's call this something else, let's say gamma. And this is also constant. Let's call this something else, let's say epsilon. So the wave, the pressure variation that we have as a result of this now is something like this. The net pressure two P naught. Now I'll write these terms in reverse order. Cos omega 2 minus omega 1 by 2 T plus epsilon into sine omega 1 plus omega 2 by 2 into T plus delta gamma, let's say, okay. So I mean this whole term I'm writing as minus. So now what we can understand that this term omega 2 minus omega 1 by 2. This is 2 pi into f1 minus f2 by 2 t. So this is basically pi into delta f, where delta f is the difference of the two frequencies. This is also called the beat frequency. And we'll understand why it is called the beat frequency. So typically it is a small value. So if we take an example where, let's say, our f1 is 198 hertz, let's say, and our f2 is 202 hertz, then delta f here. Now delta f, I mean, typically we take it with a mod value. So mod of delta f is 4 hertz. So the beat frequency is equal to 4 hertz here. Now we'll understand why we call this the beat frequency in just a moment. So actually the beat frequency becomes mod of delta f. Whereas omega 1 plus omega 2 by 2 basically equal to 2 pi into f1 plus f2 by 2. So it is 2 pi into, you can say, f average. So here for this one, it will be 200 hertz. So in this particular example, for this example, the term will become like this: 2p naught cos 4 pi t into sine 2 pi into 200. Okay. So in a term like this, what happens is that we club these two together, because, or basically before this, we'll write this like this now. So this is becoming what we do is we understand that this term here is a slow change because delta f is small in value. So what it does is this creates a periodic variation in amplitude. So we take the amplitude of the wave as 2p naught cos pi delta f. So this term's mod is the amplitude. So this amplitude is periodically varying between 0 and 2p naught at a frequency equal to delta f. Even though this term is pi and not 2 pi, but it's a mod cos function. Okay. So the thing to understand here is that mod cos theta has a period of pi. Okay. So mod cos pi delta f into t will have a time period of delta f. Sorry, we'll have a time period of 1 by delta f, or a frequency of delta f. So what happens in this case, and this other term f average is the frequency of the sound heard, that becomes f average, which is f1 plus f2 by 2. So the tone of the sound that you are hearing, remember frequency is to do with tone, that is of this frequency, okay, whereas the amplitude is to do with loudness. So amplitude or loudness or intensity of the sound that you are hearing, that is periodically varying between very soft sound to comparatively loud sound at a frequency equal to this. That's why this is called the beat frequency. So I'll just minimize this and note down these points. Then we'll understand this through a visual picture also. Just a couple of more minutes, we'll complete the lecture. So in this particular example that we have, you can see that the amplitude is equal to mod of 2p0 cos 4 pi t plus whatever this epsilon is. So we can see that the beat frequency is equal to 4 hertz, and the frequency of sound heard is 200 hertz. For this particular example, where f1 and f2 are like this is the frequency of sound heard, and this is the beat frequency. Yes, I'm scrolling up a little bit. We'll come back to this. So I won't be teaching anything after this. So we have completed this. Okay. So this is the complete description of beats. So with this, we'll complete today's lecture. So see, the net amplitude becomes this term. So this delta f is a small frequency, because that's the difference in f1 minus f2. So small frequency means that it's a slow change. So the net amplitude is such that it's slowly changing between 0 and 2p naught rhythmically or periodically at a frequency equal to delta f. Whereas the actual tone of the sound heard, which is the frequency of the sound heard, is according to this sine 2 pi f average term, where the frequency is the average of the two. So that's why, for example, if we are mixing two tones of 198 and 202 hertz, the actual frequency of sound we'll hear will be 200 hertz. But because it's a mix of these two, we'll also hear the loudness of the sound varying with a rate of 4 hertz. It will not have a continuous loudness, or it will not have a uniform intensity, but the intensity will periodically vary between very soft and comparatively louder at the rate of 4 hertz or 4 cycles per second. So you'll hear a kind of wobbly sound in terms of the loudness. It will not be uniformly loud. Okay, so that's it with today's session. Okay, we will discuss Doppler's effect in the next lecture, and with that we'll complete sound. Next, after sound, we'll be doing optics. So most probably in the next lecture, after completing Doppler's effect, we'll move on to geometrical optics. That's it for today's session, people. Wish you all the best.
Bye, sir. Thank you, sir.
Bye,
Sir?
sir. Thank you.
Thank you, sir. Bye, sir.
Sir, could you explain the slow change again?